We're going to go to the business part of the enzyme and really look at the active site. First, we're going to see how we determine what's going on in the active site, and then we're going to look at an example. Now, to understand what's going on in the active site, we need to know which amino acids are there at the active site and how they are in a spatial relationship to each other. So we identify the amino acids, the spatial relationships, and then we look at the mechanism. What steps are involved? And again, we are going to consider chymotrypsin. And chymotrypsin, again, catalyzes the breakdown or hydrolysis of peptides near phenylalanine or tyrosine residues. Now, a little bit about chymotrypsin again. We use p-nitrophenylacetate as a model because it's easily followed by spectrophotometry. I think one of them is colored and one of them is not. I'm not quite sure. But what they realized, so they used this as a model because we have an ester bond and we have something that's hydrophobic here. So it does a good job, and our enzyme chymotrypsin does work to cleave that. So what they did is they used it as a model, and they found that the mechanism by which chymotrypsin works to cleave this ester bond is a two-step process. First, the enzyme is going to form a covalent bond with the carbonyl of the ester. So it's going to cleave the ester here. It's going to release half the molecule. Then after it's released half that molecule, then we work to disentangle or cleave the bond between the enzyme and the carbonyl part. And so then we're left with the free enzyme and the other half. So again, in this model molecule, what we're doing is we're cleaving. We're breaking a bond. And the way that the enzyme does it is first to form a covalent bond with the carbonyl, then and release the other half of the molecule. And then what we do is we cleave that. Now, what they found by monitoring how much and when the kinetics of the release of the p-nitrophenolate, or one half of the molecule, and the other half. So what they did is they monitored for this guy and for this product. So both of those products. And they found that this first reaction was very quick. We had a burst. And then there was a sort of lag where we weren't getting acetate for a while until this burst was over. We had basically built up enough of this to push this reaction forward. Okay? So it's a two-step process. Now, so we figured out somewhat of the mechanism using that model. But we really want to find out which amino acids are going to be at the active site. And basically what we do is we find ways, so say, here's our enzyme and here's a serine residue. And by looking at the structure, scientists figured out this one might be at the active site. So what they're going to do is put a piece of masking tape over that one amino acid residue. So the masking tape is DIPF in this case. And it binds and sort of covers up our serine amino acid residue. Now, we've got to make sure that the enzyme's structure isn't changing. That by putting that masking tape over that amino acid residue isn't changing the conformation. So what they do is they do structural studies before labeling, and then they do structural studies after they label. And they find that the enzyme has not changed structure. The active site still looks like it does, but we put a piece of masking tape over that serine residue. And once they did that, they realized that the enzyme does not work anymore. They inactivated it. So by putting a piece of masking tape over this serine 195, you've rendered the enzyme inactive. So they know that that serine has something to do with the mechanism. They also found that a histidine in position 57 is also involved at the active site. They labeled the active site with TPCK, which you're going to have to remember the name and the structure. Just joking. I'm sorry. That's ridiculous. I just want you to remember masking tape. Okay? That's all right. Okay. I'm not going to ask you what they used. That you cover the amino acid with something, a label. Okay? If you use tape in your answer, I'm fine with that. Okay? They cover the amino acid in question with something. And once they labeled it with this guy and made sure that the enzyme didn't change its structure, then they realized the enzyme was not going to be active. All right. One thing is that this group is much like our substrate with this phenyl group. So because the serine 195 and histidine 57 are required for activity, put a piece of tape over them, the enzyme doesn't work, then they have to actually be sterically close to each other. In space, they have to be close. And so what they did is some X-ray crystallography, and they showed that they were close to each other. I'm not going to go over this, but there is another aspartate that is also involved in the catalysis. And so chymotrypsin must be folded so that these two, or these three, are close together. And we have an active site. We sometimes say pocket. So here, the two that are really important are the histidine 57 and the serine 195. We know that serine 195 and histidine 57 are at the active site. So we're showing you space is the orange, and then the green is the peptide chain. So we're showing you where the serine and the 15. So this is sort of like the two phases. So the top is that slow phase, and the bottom is that second fast stage. So what we have here, this one is our substrate. Serine has an OH. It's actually CH2OH. Histidine has this ring with the nitrogen on it. And in this amino acid, we have some hydrogen bonding going on to maintain the tertiary structure. And what's going on here is the nitrogen of the histidine is hydrogen bonded to the hydrogen of the serine. When you see a serine in a amino acid sequence, think that's probably hydrogen bonding with something, an OH. And then the nitrogen is that has the electron pair that will hydrogen bond. So this dot, dot, dot is hydrogen bonding. All right, let's talk about the substrate now. What is this called? The CN bond.
Amide.
Yeah, an amide or a peptide bond. Now, R1 is going to be a hydrophobic side chain. It's going to be an amino acid with a hydrophobic side chain. So it fits into our hydrophobic pocket. So right here, this is our hydrophobic pocket. Now, those of you that have not had organic chemistry, just kind of go along for the ride. Those of you that have had organic should be able to really understand what I'm saying here. All right, so, and I think we've covered enough for everybody to understand, but it will be more apparent to those that have had organic. So what we have is that the bond between the oxygen and the hydrogen is weakened by this hydrogen bonding. So this oxygen is a nucleophile, and it is going to nucleophilically attack the carbon of the carbonyl. Remember when we were at the beginning of the semester, all this stuff that we were learning at the beginning of the semester is coming together right here. So here we have the hydrogen bonding, we have the nucleophilic attack of the oxygen on the serine to the carbon of the carbonyl. That carbon of the carbonyl is partially positive because carbons of the carbonyl, C double bond O, are partially positive. The oxygen is partially negative. Go on, what's your question? Oh, you got it? Okay. So what we have is then the nitrogen is going to take that hydrogen during this nucleophilic attack. We're going to create a covalent bond. So this bond right here is a covalent bond. Now there's hydrogen bonding between this hydrogen and both the serine oxygen and the peptide nitrogen. Look at this carbon. It's pretty angry. By angry I mean unstable. It's an unstable tetrahedral intermediate. Why is it unstable? Look at the carbon. The carbon that was the carbonyl has the alpha carbon attached to it that's in that hydrophobic pocket, has a nitrogen, an oxygen, and another negatively charged oxygen. Not happy. Okay, that's too much going on for a carbon. It's going to break down pretty easily. So what happens is we're going to break this peptide bond because that negative charge on that oxygen is going to fold in to make a double bond. So we're going to break this. Now, why does it want to make that double bond rather than have these 4 bonds? It's because when you have a double bond, that double bond resonates and is more stable. So this product here is more stable than this tetrahedral intermediate. That's why this bond will break. Remember, to break a bond needs energy. The way I look at what's happening with this enzyme is, have you guys ever tried to open a can and you just can't do it? And then you have your 13-year-old daughter try to open it after you, and she goes, all right, well, you don't have 13-year-old daughters, but somebody like that, and that happens a lot to me. But what it's doing is it's getting that mostly opened. Okay, it's getting it almost there, so that the reaction is a lot easier for it to happen. So the 13-year-old can come by and open it no problem. Where I was the enzyme and I got it almost all open. So here, breaking this bond by having the enzyme form this tetrahedral intermediate that's very unstable makes breaking this carbon-nitrogen bond so much easier than if it were just out on its own. Okay, so it's really getting it almost there. And then because this product is more stable, it's going to happen. So what we've done is we are breaking that bond. Now this is our slow step. So and then this half of that peptide bond goes away. So let's just review. We have the substrate, our peptide, comes in. The serine acts as a nucleophile by attacking the carbon of the carbonyl. What is this histidine acting as? It's accepting a proton. What accepts a proton? Base, right? Then what's it doing over here? It's donating a proton to the other side. So it's acting as an acid. So our serine is acting as a nucleophile, and our histidine is acting as an acid base. Why is serine acting as a nucleophile? Because the oxygen is attacking the carbon of the carbonyl on our peptide bond. Why is the histidine acting as an acid base? Because it's accepting the proton from the serine and then donating it later. So at the end of our first stage, we've chopped our substrate. We've broken that amide bond. But the other half is stuck. It's stuck in there. All right? Second stage is getting that back out, because part of running a enzyme catalyzed reaction is that you get the empty spot back again, right? You get that enzyme free to work again. So we've got to get this out. What happens? Water comes in. So in the second stage, water comes in, acts as another nucleophile. What do we have here stuck in there? What functional group is this right here that I'm circling? Ester. I heard someone whisper. Whoever did that, I'm not going to call you out, but there's a gold star for you after class. So that's an ester. Esters, I said, they are very susceptible to hydrolysis. Hydrolysis means we're going to break that ester bond with water. So this is what's happening in the second stage, hydrolysis of an ester. So in the hydrolysis of an ester, the oxygen of the water acts as a nucleophile to attack the carbon of the carbonyl. Remember, this is the whole idea that carbon of the carbonyl is partially positive, and then it then breaks this, but the oxygen of the water is an even better nucleophile because the histidine will hydrogen bond with that nitrogen, pulling it away from the oxygen. All right. So then we have another second tetrahedral intermediate. And then it's very much like this one above. The only difference is now it's with another oxygen. All right? Instead of a nitrogen there, we're going to break this covalent bond instead of this one. All right, we're going to break this one, and we're left with this that floats out. And where are we at? We're back with the same structure. So here at the second stage, the oxygen of the water acts as a nucleophile, where the histidine is hydrogen bonding. We're covalently bound to the serine. Yes?
Is the chymotrypsin shape changing as it goes through those stages before it gets back to where it is?
It is not changing shape. It is not changing shape. I don't believe that there's a total. Chymotrypsin is, this is very important, chymotrypsin is non-allosteric. So it doesn't change shape. Here, we switched gears from talking about the non-allosteric and allosteric, and that's a really good and a very important point. Chymotrypsin is non-allosteric. It's a single amino acid residue. It was our example of non-allosteric, where HECase was our example of allosteric. And so here we're just using the chymotrypsin as an example of what do amino acids do in an active site. What can they do? This is just another example of looking deep inside the active site. How do amino acids work there? This one's a little bit special because it's actually forming a covalent bond. So the serine had formed a covalent bond as a result of that nucleophilic attack. The histidine, again, is acting as a base here, and then later as an acid after the formation of the second tetrahedral intermediate. This one, I feel that the second stage is probably faster than the first stage because this is even more unstable. You have 3 oxygens around here, where you only have 2 and then a nitrogen, which is slightly less electronegative. But here, I feel that this oxygen can nucleophilically attack this pretty easy. An ester to break down is pretty easy. So that's why the second stage is faster. So we're going to break this ester bond, and then here is the other half of our molecule, the other half of our substrate that is going to leave. And we are left with our enzyme that is working so well. All right, I'm going to have to repeat the second stage in the next class. And then before, so we will end with talking about how those two were basically the 2 types of catalysis that we see very often, general acid base and nucleophilic substitution. I'm not going to get into the SN1 and SN2 because that's for your reading and enjoyment. So, which one acted as a general acid base in our example? Histidine with that nitrogen, all right? And then, which one acted as a nucleophile? the serine metals or cofactors and enzymes can also act as catalysts. They can act as a Lewis acid or Lewis bases. Remember, if you don't recall, the definition of a Lewis acid is in terms of electrons, and it's just the opposite of what it would do with a proton. So acids are proton donors or electron acceptors. So that's the way I remember it. So a Lewis acid is an electron pair acceptor. So you can see that this zinc, it's accepting electron pair from the oxygen. So it's acting as an electron pair acceptor. And so we see magnesium, zinc, manganese. They are what we say cofactors in our enzymes. There's a lot of enzymes that need them for activity. This one is carboxypeptidase A that requires zinc in the positive 2 oxidation state for activity. And so we have is imidazole side chains of histidines, and our carboxylate group of a glutamic acid will form some coordinate covalent bonds with the zinc, and then there will be another free one to interact with this this oxygen on the substrate. So this what this is going to do is sort of get this carbon even more ready for nucleophilic attack. It will make it even more positive for nucleophilic attack.